Hi, my name is Martina Olsson and I work as a PhD student within the area of advanced nano at Chalmers. Today I will talk about my research where I use X-rays to investigate the structure of different materials and specifically perform imaging with nanoscale resolution. X-ray imaging is a very versatile technique for material science, and it can help us to understand the interior structure of a material. But the most common association when talking about X-rays is its use in medical imaging. So to introduce the topic, I will start by showing you one example when X-rays helped me after a climbing accident and I fell badly on my ankle. After injuring my ankle, the hospital performed an X-ray scan to see if anything was broken. An X-ray scan is made by illuminating the object with an X-ray beam. X-rays are an invisible form of light, and as it passes through the ankle, it will interact with the material inside it. The bone in the ankle has high density, and it will therefore absorb more of the beam, while the tissue around it will absorb less. On the other side of the object, the exiting X-ray beam is collected, and what you get out is a projection image, or a shadow image of the interior structure of the object in the beam. In my case, it means that we see a shadow image of the ankle where the bone shows up bright due to the higher density of the material, and the tissue around it shows up dark. With only one projection image, it can be hard to spot a crack in the bone, as small features can easily be averaged out. And to get a more detailed image, a 3D imaging technique called X-ray tomography can instead be applied. This is also sometimes referred to as making a CT scan. In X-ray tomography, we are collecting multiple projection images while rotating around the sample. This means that you will end up with a collection of images taken from multiple angles around the sample. With these images, we can then with mathematical operations reconstruct back the full 3D volume of the image sample. In this video, you see the result of such a measurement. It shows the 3D reconstruction of my foot and ankle, and we can here zoom in on the shin bone, which is the injured part. When we now look at it from this perspective, we can clearly see a crack going up through the bone and through the full width of the shin bone. So by using X-rays, it was confirmed that my ankle was broken. This was one example that shows the strength of X-ray tomography and why it is so important to be able to look at the inside of a material without opening it up. This is one of the biggest advantages with X-ray imaging, but medical applications is just the start of what X-ray imaging can be applied to, and the same principles can be used for material science. One advantage when we go from imaging humans to materials is that we can increase the radiation dose and how many photons we radiate our sample with. This makes it possible to increase both the resolution and speed for taking images, and it makes it possible to also measure materials for nanoscience applications. I will now show one example of how we use this in my research for better understanding a pharmaceutical dosage form. In this project, we wanted to use X-ray imaging to better understand the drug release mechanism of a pharmaceutical formulation that is designed to provide a controlled drug release. When we take a medication, we want a dose that lies within a concentration range that is high enough to give an effect, but we don't want to reach a toxic concentration and get unwanted side effects. Controlling the drug release from a medication is important both to make sure that the drug concentration doesn't get too high, but also because we sometimes want to get a prolonged release and keep the drug concentration at a stable therapeutic level without the need of constantly taking a new tablet. One strategy to achieve a controlled release is to mix a drug component within a polymer matrix. By doing this, we alternate the dissolution characteristics of the drug to also depend on the dissolution characteristics of the polymer. Annette Larsson's group at Chalmers have developed a variant of such a formulation, where you instead take two different polymers that phase separate and create a two-phase polymer matrix. The key idea behind this material is that you have one polymer that is hydrophilic or water-soluble and one which is hydrophobic or non-soluble in water. This means that when the tablet is exposed to water, only the hydrophilic phase will dissolve, and the phase-separated morphology will provide a geometrical effect on the dissolution characteristics. This means that it will affect how the drug diffuses out from the material, and to understand the drug release mechanism, we therefore want to get a 3D image of the phase-separated morphology created by the two polymers. In these formulations, the phase-separated domains have a size in the range of nanometers to micrometers. So to resolve the interior structure of this material, we need to perform X-ray imaging with very high spatial resolution. To perform 3D imaging of these materials, we are again using X-ray tomography. But here the technique is adapted to achieve a high resolution, and the experiments are therefore performed at a synchrotron facility. A synchrotron is a particle accelerator where electrons are accelerated in a ring to nearly the speed of light to generate high-quality X-rays. This allows us to reach resolutions down to tens of nanometers and get a detailed image of the interior of our material. So similarly as we could use X-rays to extract the interior structure of a broken bone, we can now use the same technique for the material of our pharmaceutical tablet. Here we resolve the different phases in the material, and what we measure is the difference in electron density, and we can see a bright phase corresponding to the insoluble polymer phase and a dark phase corresponding to the hydrophilic domains that will be dissolved upon hydration. To learn more about the material and how the pharmaceutical tablets work, we measure different samples to compare the different internal structures to the release properties of the material. Here we investigated how the morphology is affected by the fraction of hydrophilic and hydrophobic polymer and how it influenced the drug release rate. To understand the structure, we need to look at the sample in 3D. In these images, we have segmented out the hydrophilic phase, and the volume renderings show a cross-section of the image volume of the samples. As this phase will be dissolved when digested, we can get a better understanding of how the drug diffuses and also relate it to the drug release properties. In these illustrations, the hydrophilic domains are colored after their size. This means that the bigger domains will be colored in yellow, while the smaller domains are colored in a deeper blue. What these images can show us is that the sample that has a larger fraction of hydrophobic polymer have more narrow and more tortuous domains. The one with more hydrophilic polymer instead creates larger connected channels and can provide a faster drug release. This was one example showing how X-ray tomography with nanoscale resolution can be applied in material science. But it can be used for almost any material, all from organics to metals and for many different scientific purposes where you want to examine the interior of your sample with a high resolution. If you want to know more about X-ray imaging and about this project in particular, the link to the article of this work is included in the description below this video. Thank you for watching this small talk.